I wanted to give some clues about how to get started on this modeling with algebraic expressions task. And first of all, just take a look at these three figures, and hopefully you can see that they have some similarities, and we're trying to actually generalize this pattern. These are specific figures: figure 1, figure 2, and figure 3. And we want to generalize this by considering the nth figure. What that means is here, n is equal to 1, and here, n is equal to 2, and here, n is equal to 3. So we have some specific examples, but we want to generalize. We want to draw this thing and represent the number of tiles in it just based on that variable n, the figure number. So the first issue that students have, I think, that I see a lot with a problem like this is that they want to start making up all kinds of variables, the length and the width and the height, and look, there's one variable in this problem, n, and that is all. And you can describe the number of tiles it takes to make the nth figure just in terms of n, and that's what we're going to work to do. I also gave some other clues here in the introduction to this problem. I asked 3 questions about these figures. Do you see a rectangle with a piece subtracted? Do you see a square and a rectangle added together? Do you see a big rectangle and a small rectangle added together? And it says to think about these different descriptions in order to pursue this problem. Because really the idea down here is to think about one of those 3 patterns in each of these places, and then to demonstrate that they're equivalent in the final question here, number 4. So I like to think about the first one where it says a rectangle with a piece subtracted. Surely you can see a rectangle with this little corner subtracted. And in each of these figures, you can see a full rectangle and a little corner taken away from that. So I call that a subtractive model, because we're actually subtracting away a piece of the full rectangle. And then these other 2 are additive models. Do you see a square with a rectangle added, a square and a rectangle added together? Well, here's a square and here's a rectangle, and we put them together. Same, here's a square and here's a rectangle added to it. Even this one, there's a little square right here, and then a rectangle added to it, which of course a square is a special case of a rectangle. But that's another way to think about it, and that's an additive model. And then, maybe you divided it up this way: a big rectangle and a little rectangle. A big rectangle plus a little rectangle. That's another additive model that's different. So our goal is to represent that, just one of them right here. And I'm gonna give you a clue about how to do that, and what I mean when I say to draw and label a diagram of the nth figure. So I saw a lot of students trying to draw all these little squares, but that's not how you draw the nth figure, because you don't know how many squares there are. You don't know what n is. Think about the border problem, which we did at the beginning of this unit. First, we had a border that was divided up into little squares, and you could actually count the number of squares if you wanted. But when we generalized, we just drew like a big square with a little square inside. We didn't actually try to divide it up into little tiny tiles, because you don't know how long each side is. It's just n. So that's what we're trying to do here. I'm going to pick one of these. Let's see. I'm going to pick one that is this second one, a square and a rectangle added together. And that's how I'm going to represent this figure right here. So here's my square, and then the rectangle comes down like this, and that's my nth figure. I can't divide this up anymore, because I don't know how many little squares are in each of these, because I don't know how big n is. But now I'm going to try to describe the dimensions of these 2 shapes based on what I see up here. in these examples, okay? And so one of the things I notice about the square is it has it's 1 squared here, 1 by 1, and in this diagram it's 2 by 2, and that's figure 2. And here it's 3 by 3, and that's figure 3. So I know that the dimension of this square, the length of that side is n. And the length of this side is also n. Notice how carefully I dimension my diagram. There it is. And then I'm going to also consider this little rectangle now. And one of the things I notice is that this dimension is always the same in every single one of these diagrams so far. It's just 2, 2, 2. It's always 2. So this dimension is 2. And the last dimension I need in order to fully describe this system, this diagram, is that last dimension. And it's, you might have to think about it for a minute, but it goes from 2 to 3 to 4 in these diagrams. So it's really just one more than n. And that makes sense also because we know that this dimension is n, and we're just adding one more unit to it. So this is n plus 1. And now I have drawn and labeled a diagram of the nth figure. Beautiful. And then I have to write an algebraic expression that gives the number of shaded tiles in the nth figure. Basically, and I could add in, if you like, this little piece that I'm not considering, but I want to know the area of this shaded region altogether. And I'm going to call this thing rectangle and this thing square in my diagram. And over here, I'm just first of all going to write the area of this. Well, the area of the square is just n squared. And then I'm adding to that the area of this rectangle, which is 2 times n plus 1. So that is my algebraic expression that gives the number of shaded tiles in the nth figure. Now it says annotate your expression to show how it's related to the figure that you drew. Well, I'm going to use my labels, and I'll just say that this is the area of the square, and this is the area of the rectangle. And that's it. I annotated it. And that's my expression. So I'm not going to complete this problem, but I want you to think about these other ways of representing this shaded region, right? The rectangle with a piece subtracted, and the big rectangle and the small rectangle added together. You could pick any one of those, draw a similar diagram, and write an algebraic expression here. And you'll get something that looks different than this because your diagram's different. And then you can demonstrate that these two expressions are equivalent right in this space below. And the way you do that is you start with one of them and you use our algebraic techniques to rewrite that expression until it looks like the other one. That's how you demonstrate that two expressions are equivalent. I hope that helps you get started on this task and helps clarify what I mean about the nth figure, how to draw it, and how to write an expression and annotate it.